Hello guys, in this video I'll uh, define impulse. I'll tell you its all properties, its units and the practical applications of impulse. So starting from its definition. So impulse is defined as the product of J. Impulse is denoted by J first of all, and it is defined as the product of F delta T, where F is a very large force acting for a very small time. So, when some very large force acts on a body for a very small time, then that force is known as impulsive force. This F is also known as impulsive force. Now, this is impulsive force. So, this is F, and the time for which this F acts is delta T. So, this delta T is the time for which this force acts. So the product of this force and the time for which it acts is combinedly known as impulse, and it is denoted by J. Now the impulse is a vector quantity, and we all know that the force is also equal to the change in momentum, and therefore F dt is also equal to dp, where dp is a change in momentum and f dt is also the impulse. So this is the impulse momentum theorem. This is impulse momentum theorem, which says that impulse is equal to change in momentum. So this is the impulse momentum theorem. So impulse is actually the change in momentum, and this change in momentum is due to a very large force which acts for a very small period of time, which is also called as impulsive force. So impulse is not the force. In fact, impulse is the change in momentum. Now the unit of impulse is equal to the change unit of momentum, as it is equal to the change in momentum, and the unit of momentum is kilogram meter per second. So this is the unit of impulse, and its direction is in the direction of impulsive force which acts on the body. Now let me tell you some practical examples that in cricket, while some fielder catches the ball, he tends to take his hands in the backward direction so as to minimize any injury on its hand, because while he is taking his hands in the backward direction, the change in momentum is constant, and it is irrespective of the fact that whether he is catching the ball with still hands or whether he is moving his hands in the backward direction. But momentum of the ball is change in momentum of the ball will be constant, because ball is coming towards him with a certain momentum, and finally the ball achieves the rest position. So the change in momentum of the ball is constant. But in the case when he catches the ball with his still hands, the time taken for this change of momentum of the ball is very small, and if that delta p is constant, and it is equal to f1 into delta t1, and it is also equal to f2 into delta t2. So in the first case, if this time is very small, then this force has to be large. And in the second case, when the boy takes his hands in the backward direction while catching the ball, this time in which he has allowed the momentum to change is large by taking his hands in the backward direction. So the force that is required to change that momentum is small. So by applying a small force on the ball will give the reaction back to the hands of the fielder, and that reaction would also be small, so that he could avoid any injury. So it is better to catch the ball while taking the hands in the backward direction, so as to allow a greater time for the change in momentum of the ball, and which will require a lesser force to change that momentum. So ball will also apply the less force on the hands in reaction to the applied force on the ball. Now, let us also discuss another example that in vehicles, while they move on the road, shockers are provided, because while vehicles move on the road, there are many pits and holes on the road, due to which it makes a bumpy ride. So if by providing the shockers increase the time in which the momentum changes of the vehicle, and the shockers provide greater time of contact for the tire and the pit, so that the change in momentum in vertical direction takes a greater time, and due to that greater time, the force applied by that road on the tire is lesser, and the damage on the car is also avoided. So this is the reason due to which the shockers are provided in the car. So there are many examples by which you can understand the impulse, and I would also give you another example in which, when you fall on a marble floor from certain height, and when you fall on a sand from that particular certain height, same height, then the injuries would be more, and very dangerous injuries would occur on falling on the marble floor, because on marble floor the change in momentum has been done in a very less time, so that very greater amount of force is required to change that momentum in less time. But in sand, the change in momentum is done in a greater amount of time, so less amount of force is required in the case of sand to change that momentum, and therefore by requirement of less force, the injuries which would occur to us would be also lesser in the case of the sand. Now let us discuss the impulsive forces first. A force which has a very high magnitude and which acts for a very small period of time is called as impulsive force. Now gravitational force and spring force are always non-impulsive, and the normal reaction and friction can be impulsive and non-impulsive both. Now the impulsive force is always balanced by an impulsive force. It is not possible that an impulsive force is balanced by a non-impulsive force. So let us see some examples of impulsive forces. So in this first diagram, you can see that these blocks will collide with each other, and the normal reaction Ni will act in this direction. And this normal reaction on each block, which is given by them by the floor, and this normal reaction is balancing their mg. So you can see that this normal reaction, which is due to the impact, is a very large normal reaction, and it is acting for a very short period of time, and it is acting for only that period of time in which the impact is occurring. So there is no change in the magnitude of the normal reaction N1g and N2g by the impact, so they would remain constant always, and they would act continuously. So the impulsive force is impulsive normal reaction in this case is Ni. This is impulsive, and the normal reaction, this N1g and N2g, is non-impulsive. Okay, so this is the case. Now in this case, first case, this ball strikes this second ball. You can see at the time of collision, there is a huge normal reaction which would be developed between these two balls, which is N1, and due to that normal reaction which is provided by the floor to this ball will also increase for a short period of time. Therefore these two normal reactions are very high forces which are acting for a short period of time, and the time for which they are acting is only the time of the collision. So they both are impulsive forces. Both N1 and N2 are impulsive forces. But in the second case, you can see that when these balls will strike each other, then there would be a greater normal reaction N1 which would be developed due to the impact, and this N1 would add up in the mg of the smaller ball, and due to this N1, N3 will also increase. So N3 and N1 are the larger forces which are acting for a very short period of time, but N2 is not an impulsive force because N1 is acting in the opposite direction of N2, and like that, and therefore a component of N1 would decrease this N2. So N2 would be a decreased force, and hence it would not be an impulsive force. So this is non-impulsive, and this force N3 and N1 are impulsive. Now in the next diagram, you can see that during the collision there is a huge force which is developed, and this force is N1, which is the contact force between these two balls, and due to this N1, this N2 would also increase. Therefore in this case, both N1 and N2 are impulsive. Now, impulsive tensions are the tensions which are developed in the rope. When we create some jerk in the rope, then equal and opposite tensions suddenly starts to act on each end, and therefore equal and opposite impulses are applied on the bodies which are attached to both ends of the string. So when one end of the string is fixed, then impulse is acting in both ends, but the impulse acting on the fixed end cannot change the momentum of that fixed end, but the impulse acting on the free end can change the momentum of the object which is attached to the free end. So when the string is attached from both its ends, then the impulse changes the momentum on the both ends, and this is the impulsive tension. Now you can see that there is a big ball which is hanging from a rope, and that rope is attached with a roof. Now when this small ball A will strike this ball, then the momentum transferred by this ball A is in this direction. So the impulse which this ball A will apply on this bigger ball is in this direction. So to balance out this impulse, this one, the tension in the rope would have to increase, and therefore when this ball A will strike the bigger ball, then the tension developed would be impulsive. But when ball B will strike in this direction, then there would be no effect on the tension, because tension is acting in the vertical direction, and the impulse of this ball B is acting in the horizontal direction. So there would be no change in the tension of the string. So in that case, it would be a non-impulsive force. And when this ball C will strike from the bottom, then the impulse which C would apply is in upward direction, and it would decrease the tension. So also this tension would be non-impulsive because its magnitude is less. So this is the case of impulsive tensions. Now in this case, we'll discuss the impulsive friction. So you can see that there are two rough surfaces in this case, this one and this one, and the friction purely depends on its normal reaction. So if these normal reactions are impulsive, then their friction would also be impulsive. And obviously you can see in this type of collision in the vertical direction, these two normal reactions N1 and N2 will be impulsive, and hence both the frictions which are acting on these two surfaces would be impulsive. But in the second case, when the collision is occurring like that, so this friction, which is this normal reaction, would be impulsive. This normal reaction would be non-impulsive, which we have already discussed, and this normal reaction N1 would be impulsive. So the friction acting between these two surfaces would be impulsive. The friction acting at this surface would be impulsive, but the friction acting at this surface would be non-impulsive. So this is the case of impulsive forces, impulsive normal reactions, impulsive tensions, and impulsive frictions. So we'll discuss the numericals which are based on the impulse in the next video. Thank you.